You ever get the feeling that the more we learn about the universe, the less we actually understand it? We've mapped the cosmic microwave background, sent telescopes deep into intergalactic space, and even detected ripples in spacetime. We've written entire books explaining the laws of physics, charted galaxies billions of light years away, and modeled the beginning of time itself. But then, something weird shows up. A cold patch in the sky that shouldn't be there. A star that flickers for no reason. Entire regions of space that look too empty, or too aligned, or just wrong. And suddenly, all those neat models and elegant equations, they start to feel a bit fragile. The truth is, there are things out there right now that we can see, measure, and study, but still can't explain. Not even close. Not with dark matter, not with quantum mechanics, not even with the usual maybe it's aliens fallback. Just real, observable mysteries that science hasn't cracked yet. And we're not talking about vague speculation or made-up stories. These are real data points, verified observations, things that keep showing up in our instruments and keep confusing the smartest people in the room. So in this video, we're going to explore them. Not just the strange, but the truly unexplained. The things that make scientists pause, scratch their heads, and say, okay, what is that? Some might turn out to have answers someday, some probably won't. But either way, they tell us something important, that the universe is still way ahead of us. And maybe it always will be. If you take a map of the oldest light in the universe, the cosmic microwave background, or CMB, it mostly looks like static. Just tiny temperature differences, scattered all across the sky, almost too subtle to notice. And that's what scientists expected. Small random fluctuations. Nothing too extreme. But there's this one spot. It's unusually cold. Not just slightly colder than average, but noticeably out of place. It stands out like a dark patch on an otherwise even wall. And for years, no one's been able to explain why it's there. This region, called the cold spot, was first picked up by NASA's WMAP satellite in the early 2000s. Then, the European Planck satellite came along and confirmed it in 2013. So this wasn't a sensor issue or an error in processing. It's there. It's real. A massive elliptical region in the sky, about 1.8 billion light-years across, located in the constellation Eridanus. A true anomaly in cosmology, colder than everything else around it. And not just cold in the usual sense, cold in a way that doesn't quite fit the pattern. In theory, the early universe should have been almost perfectly uniform. The tiny temperature differences in the CMB are what led to the formation of galaxies and clusters. But even those differences follow a statistical pattern. The cold spot, it doesn't. So people started asking, could something be blocking or distorting the light? That led to the supervoid idea. Maybe there's a massive region of empty space between us and the cold spot. Something so underdense that it causes the light to lose energy on the way to Earth. That could, in theory, make the area appear colder than it really is. And yes, there is a void in that direction. But it's not big enough. It doesn't go deep enough. If this cold spot were a dent, the void is barely a scratch. So, that explanation, while interesting, doesn't really solve it. Another possibility. Maybe it's just a fluke, a one-in-a-million coincidence, something that happens in a random universe, just by chance. But that's a tough pill to swallow when you're dealing with data that stretches across billions of light years. Scientists don't love hand-waving away anomalies with luck. Then there's the more extreme idea, the one you'll hear in documentaries and late-night science forums. What if the cold spot is something more than a random dip in temperature? What if it's a sign of something beyond our universe? A bruise left behind by a collision with another universe, maybe during the inflationary period right after the Big Bang. Some physicists have floated that possibility, not as science fiction but as a serious, if speculative, explanation. The idea is that if our universe ever bumped into another bubble universe during expansion, it could have left behind an imprint, like this. Now, that theory isn't mainstream. It's a huge leap. But the fact that people even consider it shows how baffling this cold spot is. It doesn't play by the usual rules, and that's why it stayed on the list of the universe's weirdest mysteries. It's not just cold, it's unexplained. And for now, it's a reminder that even the background of space, the most distant ancient light we can observe, still holds surprises that don't fit our models. You'd think that by now we'd have a solid grasp of how the universe moves. Everything expands outward, galaxies drift apart, and the further something is, the faster it recedes from us. That's the idea behind cosmic expansion, a concept that's held up pretty well since Edwin Hubble made it famous nearly a century ago. But then came something that didn't fit. A motion that didn't follow the expansion. A large-scale drift, as if entire chunks of the universe were being pulled towards something unseen. And not just a few galaxies here and there. We're talking thousands of galaxy clusters, all heading in the same direction, as if they're being drawn by a giant invisible force. This strange motion was picked up by astronomers in the late 2000s. By studying the cosmic microwave background and measuring how its photons are scattered by massive galaxy clusters, something called the kinetic Sunyaev-Zeldovich effect. They noticed that these clusters weren't just sitting still relative to the background. They were drifting, all in the same general direction, toward a region of the sky near the constellations Centaurus and Hydra. This movement became known as dark flow. Now, galaxies are always moving. That's normal. Gravity tugs things around, local clusters interact, and space itself expands. But this flow was different. It was large-scale, coherent, and persistent. It wasn't caused by nearby structures like the Great Attractor or the Shapley supercluster. Those were already accounted for. This was something bigger, farther, stranger. One of the biggest questions was, what's causing this drift? Because if space is expanding uniformly in all directions, there shouldn't be a preferred direction for everything to move toward. Yet the data kept suggesting otherwise. So, scientists did what they usually do: check for errors. Could it be noise in the data? Misinterpretation of how the background light interacts with galaxy clusters? Could the instruments have been slightly off? But year after year, follow-up studies continued to find signs of the same drift. The measurements were challenged, revised, re-verified, but the idea of dark flow never completely went away. Some studies found it, some didn't. Current consensus leans toward it being unconfirmed. But the original results were enough to raise eyebrows, because if they're correct, then something very big is going on. Something outside the observable universe. That's the unsettling part. The observable universe is limited by how far light has traveled since the Big Bang, about 46 billion light-years in any direction. But that doesn't mean there's nothing beyond that edge. It just means we can't see it yet. Dark flow suggests that something beyond that edge might be massive enough to tug entire galaxy clusters in our direction. Something enormous. And we don't know what it is, because it's beyond the cosmic horizon. We literally can't observe it. That's led to some wild ideas. One is that our universe isn't alone. That maybe there are other universes out there, huge, separate bubbles, floating in a larger multiverse. And maybe one of those bubbles, much bigger than ours, is close enough to exert gravitational influence. Not in a science fiction sense, but in the literal physics of mass and curvature and pull. Another idea. Maybe the early universe had structures far more massive than anything we've modeled. Massive enough to leave behind gravitational fingerprints that we're only now starting to detect. These wouldn't just be big galaxies or clusters. They'd be megastructures, the kind that reshapes space-time itself. And of course, there's the simpler possibility. Maybe we're just reading the data wrong. Maybe what we're calling dark flow is an illusion, caused by some local distortion we don't fully understand yet. That explanation would certainly be cleaner, and some newer studies lean in that direction. But here's the thing, we still don't know. Dark flow is one of those cosmic mysteries that sits on the edge of data and speculation. Some researchers have moved on from it, saying the evidence isn't strong enough. Others are still digging, running simulations, refining measurements, and trying to understand whether this is a glitch or a hint of something bigger. And if it is real, then it means our universe isn't just expanding. It's being pulled by something beyond our cosmic sightline. Something that's there, but forever out of reach. That's what makes this one so strange. It's not just about galaxies moving, it's about why they're moving. And when the answer might lie beyond the part of the universe we'll ever be able to observe, that's a mystery with no easy resolution. Most stars behave like you'd expect. They shine, they flicker slightly if something passes in front of them, and they follow patterns that make sense. We've studied thousands of them. So when a star starts dimming in a way that doesn't follow any known rules, people notice. And when the dimming is irregular, unpredictable, and far deeper than it should be, people start getting confused. That's what happened with a star called KIC 8462852, now more famously known as Tabby's star, after astronomer Tabitha Boyajian, who helped bring its strange behavior into the spotlight. The star sits about 1,470 light-years away from Earth. And at first glance, there's nothing remarkable about it. It's a regular F-type main sequence star, slightly hotter and larger than our Sun. But what made it special wasn't what it did, it was what it didn't do. When astronomers looked at the data from NASA's Kepler Space Telescope, which spent years watching thousands of stars for tiny dips in brightness caused by orbiting planets, Tabby's star stood out. It wasn't just dimming, it was plummeting in brightness. Sometimes by 5%, sometimes by 15%, and in one case, by over 22%. That's massive. For comparison, when a Jupiter-sized planet passes in front of a star, it usually dims the light by about 1%. So for something to block 22% of a star's light, it would have to be huge. But even then, the dimming would have a pattern. It would repeat in a cycle, because planets orbit at consistent intervals. That's not what was happening here. The dimming events were erratic. No consistent timing, no symmetry, just unpredictable drops in brightness, followed by long stretches of nothing. At first, the search for explanations focused on the usual suspects. Maybe it was a cloud of comets, or a dust disk, or some kind of debris field around the star. But none of those ideas really held up. The comet theory, for example, would require an enormous family of comets, far more than we've ever observed, moving in just the right way to cause that pattern. And even then, it wouldn't explain the long-term dimming trend that's also been detected. The star appears to be getting dimmer overall, year after year. And here's the part that got the public's attention. The alien theory. A few scientists, cautiously and carefully, floated the idea that maybe, just maybe, the dips in brightness were caused by some kind of megastructure. A huge artificial construct built by an advanced civilization, orbiting the star and blocking its light. Something like a Dyson swarm, a hypothetical structure designed to capture a star's energy. Now, no one was claiming that was the most likely explanation. It was more of a last resort, we can't rule it out kind of thing. But once the idea was out there, it stuck. People were fascinated. A normal star behaving in a completely abnormal way. So abnormal that we had to consider artificial causes. That's rare. Of course, more grounded theories continued to come in. Some scientists suggested that irregular clouds of interstellar dust might be responsible. Dust that filters certain wavelengths of light more than others, causing the strange dimming pattern. Others pointed to internal stellar processes we might not fully understand yet. But again, nothing fully explains all the weird behavior. And here's the strange part. Even after years of monitoring and analysis, we still don't know what's going on. The star continues to show unpredictable brightness dips. None of the leading theories explain all the observations. The star's oddity persists, and every time new data comes in, It seems to raise more questions than it answers. Tabby's star is one of those rare cases in astronomy where all the obvious explanations fall short. And while the alien idea has mostly been set aside, the fact that it had to be brought up at all shows just how strange this star really is. So, what are we looking at? A bizarre stellar quirk we've never seen before? A cloud of material behaving in a way physics doesn't fully explain? Or something else entirely? Whatever the case, Tabby's star reminds us of something important. Even in the parts of the sky we think we understand, among ordinary stars that should follow ordinary rules, there are still things we can't explain. Things that just won't behave. We've pointed radio telescopes at the sky for decades now. We've listened for patterns, pulses, anything that might hint at intelligence beyond Earth. We've sent out messages too, long-range broadcasts, binary codes, even a spacecraft carrying a golden record with instructions and music, just in case something or someone finds it. And yet, nothing. That silence is strange, because if you look at the numbers, just the raw probabilities, life should be common. The universe is old, the number of stars is almost uncountable, and many of those stars have planets. Some of those planets are in the habitable zone, where liquid water can exist. Given enough time, life should emerge. And intelligent life, it doesn't seem like it should be that rare, not if you run the math. This idea is at the core of the Fermi paradox. If intelligent life is likely, and the universe is so big, then where is everybody? That's a question we still don't have an answer for. But it's not just the silence that's weird, it's the consistency of the silence. No blips, no long signals, no unambiguous messages, just a void. Except, not entirely. There have been a few moments that stood out. Signals that caught attention. Not because they were long or detailed, but because they were strange. The most famous is probably the WOW signal, detected in 1977 by astronomer Jerry Amon at Ohio State University's radio telescope. It lasted for 72 seconds, was incredibly strong, and came from a region of space where nothing should have been transmitting. The astronomer who saw the printout circled the spike and wrote "Wow" in the margin. That became its name. To this day, no one knows what caused it. It remains one of astronomy's enduring mysteries. It never repeated. No single explanation fully accounts for the signal's characteristics, and its one-time nature complicates verification. It came and went, like a voice in a crowd that vanishes before you can turn around. Then there are fast radio bursts, short, sharp bursts of radio waves that last only milliseconds. The first one was discovered in 2007 almost by accident, buried in old data. Since then, we've found dozens. Most don't repeat. A few do. Some come from distant galaxies. The energy they release is immense. Far more than what a star like our Sun produces in the same amount of time. And we still don't know what causes them. The best guesses. Some point to neutron stars or magnetars, exotic high-energy objects that can produce intense radio pulses. Others suggest merging black holes or extreme magnetic fields twisting space in a way we haven't modeled yet. All possible. But again, none of the current theories explain every kind of FRB we've seen. There was one case where a signal repeated with a pattern, a 16-day cycle. That grabbed headlines. Because randomness is one thing, but structure, repetition, that makes people curious. Still, even that one has been chalked up to natural causes, maybe a binary system or an object orbiting near a strong emitter. The thing is, we're not getting clear answers. We have data, we have spikes and blips and anomalies, but nothing that screams intelligence. No long message, no alien hello, just a universe that seems busy with activity, but none of it directed at us. And that raises another possibility. Maybe we're just not listening the right way. Maybe we're scanning the wrong frequencies. Maybe civilizations don't use radio. Or maybe they don't want to talk. The idea that advanced life might intentionally stay quiet, out of caution or principle or fear, is something scientists have started to consider seriously. It's also possible we're early. Maybe intelligent life is still rare, and we're one of the first to reach this point. That would make us pioneers. Or maybe civilizations rise and fall, and the time windows where two advanced species could communicate just don't line up. Or maybe life is out there, but it's nothing like what we expect. No cities, no technology, no radio. Maybe intelligence evolved in ways we can't detect. Under ice, in atmospheres, on gas giants. Maybe life exists, but it doesn't care about communicating. Whatever the case, the silence isn't just empty space, it's a puzzle. We know the conditions for life exist. We know the building blocks are everywhere: carbon, water, energy. But when we look up, we don't see signs of anyone else using them. And maybe that's what makes this mystery so strange. It's not what we hear, it's what we don't hear. Not an absence of noise, but an absence of evidence, in a universe that should be full of it. The more we listen, the more we realize. The quiet itself might be telling us something. There's this idea in cosmology that the universe should look the same in every direction. Not exactly the same, but more or less uniform when you zoom out far enough. Galaxies here, galaxies there, spreading evenly like dots on a balloon. This principle is called isotropy, and it's one of the foundational assumptions in modern physics. But what happens when the universe breaks that rule? When scientists studied the cosmic microwave background, CMB, the faint glow left over from the Big Bang, they expected to see random fluctuations, tiny temperature differences scattered without preference. And for the most part, that's what they saw. But then something strange showed up. A pattern. A suspicious alignment of low multipole moments in the CMB data. Basically large-scale temperature fluctuations that seemed to be pointing in the same direction. This alignment became known, somewhat jokingly at first, as the axis of evil. When satellites like WMAP and later Planck mapped to the CMB in incredible detail, the results were surprising because these temperature patterns shouldn't be lining up. They should be random, but they weren't. They were clustered, tilted, aligned along a specific axis that cuts through the sky. Now maybe that sounds harmless. So what if the universe has a preferred direction? But here's why that matters. If this alignment is real and not just a statistical fluke or artifact of measurement, it violates isotropy, which means the large-scale structure of the universe isn't as uniform as we thought. It could mean there's something profoundly wrong or incomplete about our understanding of the universe. And that would force us to rethink some major parts of cosmology, everything from inflation theory to the shape of space itself. The name Axis of Evil was meant to be tongue-in-cheek, but the problem it describes is serious. Scientists tried to find ways to explain it away. Maybe it's just noise. Maybe there was contamination in the instruments. Maybe our galaxy is interfering, leaking foreground signals that mess up the readings. They checked again and again. And while galactic interference does exist, it doesn't fully erase the alignment. The pattern persists. So what does that mean? That's the strange part. No one really knows. Some researchers think it could point to new physics, something outside our standard model of the early universe. Others believe it might suggest the universe is finite and shaped in a strange way. Maybe not perfectly flat, but slightly curved or twisted, like a donut or torus. These shapes can introduce large-scale alignments that mimic the axis of evil effect. And then there's the uncomfortable idea. Maybe the alignment is a clue that our universe isn't alone. If the multiverse theory holds any weight, perhaps we're seeing the gravitational imprint of another universe brushing up against ours. A neighboring bubble influencing the temperature patterns in ways we don't yet understand. Or, and this is just as likely, maybe it's something boring. A quirk in the math. A rare coincidence that only looks significant because our brains are good at spotting patterns. We don't like randomness, so we try to make sense of it, even when there's nothing there. Still, the fact that this pattern shows up in multiple datasets using different instruments makes it hard to ignore. The axis of evil doesn't break physics. It doesn't undo what we know about stars or gravity, but it does tap on the edge of something bigger. It asks a simple question that cosmologists aren't ready to answer. Why is the universe pointing that way? And it leaves us with a mystery that's hard to shake. Because if the universe really does have a preferred direction, if there's some underlying structure or bias we haven't accounted for, then everything we thought was balanced and smooth might be just a little bit off. And in a field like cosmology, where symmetry is everything, that one small tilt could mean a very big deal. If you run a simulation of how galaxies form, something odd happens. You don't just get a beautiful spiral like the Milky Way, you also get dozens, sometimes hundreds, of smaller ones orbiting around it. Little galaxies, mini halos, like moons around a planet, only made of stars and dark matter. These are called satellite galaxies. And according to models based on dark matter theory, our galaxy should be surrounded by a whole swarm of them. But when we look at the real sky, we don't find hundreds. We find a few dozen. And most of them are dim, irregular, and hard to detect. So either our simulations are wrong, or we're missing something. This is what astronomers call the missing satellites problem. It started showing up in the late 1990s, when computational power had reached the point where we could simulate galaxy formation in detail. These models, based on lambda cold dark matter, the most widely accepted cosmological model, predicted that dark matter halos should form all kinds of structures, including many smaller clumps orbiting larger galaxies. In theory, these clumps would collect gas, form stars, and become satellite galaxies. But in reality, not so much. When telescopes like Sloan Digital's Sky Survey and later Gaia looked at the region around the Milky Way, they found far fewer satellites than expected. Same for Andromeda, our neighboring spiral galaxy. The numbers just didn't match. The models predicted hundreds of small galaxies. We were seeing maybe a few dozen. That's a big gap. So the question became, where are they? One idea is that the satellites are there, but they're too dim for us to see. Maybe they didn't collect enough gas to form stars. Maybe they're made mostly of dark matter and just floating around invisibly. That would mean they're technically there, just hard to spot. And over time, we've started to find more of these ultra-faint galaxies. Thanks to better surveys and more sensitive instruments, the count is slowly increasing. But even now, the numbers still don't fully add up. Another theory is that something in the early universe prevented these small halos from forming stars. Maybe energetic bursts of radiation, like from ionization, blew gas out of the small halos before they could condense. Without gas, there's no star formation. So the structure exists, but it's dark and dead. Others think it might be an issue with the dark matter model itself. If dark matter is warmer or more interactive than we assume, maybe it doesn't clump in the same way. That would affect the number of small halos that form. In other words, maybe our whole framework needs adjusting. There's even a deeper problem underneath all of this. If our galaxy doesn't match the predictions of dark matter simulations, then how reliable are those simulations in the first place? We've based a lot of our understanding of the universe's structure on them. Everything from galaxy formation to cosmic web patterns. If they're off at small scales, are they off at larger ones too? Some researchers argue that this is just a case of observational limits catching up. That as our telescopes improve, we'll slowly find all the missing satellites. Others believe we're dealing with a real mismatch, an issue in the theory itself that needs to be resolved. And that's what keeps this problem alive. It's not just about tiny galaxies, it's about the accuracy of our models. The missing satellites problem touches on dark matter, early star formation, cosmic evolution, and even the shape of the Milky Way's halo. We don't have a final answer. The gap is narrowing, but it hasn't closed. And until it does, this mystery sits like a quiet warning. Our universe may not be behaving exactly the way we think it should. And sometimes it's the things we don't see that tell us the most. There are black holes scattered all across the universe. Most are small, just a few times the mass of our sun. Others, like the one at the center of our galaxy, are a few million solar masses. But then there's another class entirely, ultra-massive black holes. These are monsters. We're talking about objects weighing in at billions of times the mass of the Sun. And here's the strange part. We're finding them way too early in the universe's timeline. Some of these black holes existed just 700 million years after the Big Bang. That's nothing, cosmically speaking. The universe was still in its infancy. Galaxies were just starting to form. Stars were only beginning to light up the cosmic darkness. And yet, in this early era, somehow, there were already black holes the size of galaxy cores. That doesn't make sense. Because according to what we know, black holes form from the collapse of massive stars. Then they grow, slowly by feeding on gas, dust, stars, or merging with other black holes. But even under ideal conditions, it takes time. A long time. You don't just jump from a stellar black hole to one that's billions of solar masses in a few 100 million years. That kind of rapid growth shouldn't be possible. Not with the rules we've written. So, how did they get there? One idea is that maybe these black holes started bigger than usual. Instead of forming from a single star, they might have collapsed directly from a primordial gas cloud. This would skip the stellar phase and give the black hole a head start. Something we call a direct collapse black hole. It's still theoretical, but it could explain how some of these early giants formed so quickly. Another possibility is that the early universe was simply better at feeding black holes. Denser gas, more frequent mergers, and fewer obstacles might have allowed them to grow at faster rates than what we see today. Maybe they were in overdrive mode, pulling in material at speeds we didn't think were sustainable. That could work, but it still stretches the limits. Then there's the idea that our understanding of black hole physics, especially in extreme environments, might be incomplete. Maybe there are unknown feedback mechanisms or interactions with dark matter that accelerate growth in the early cosmos. Or maybe the physics of accretion, the way material falls into a black hole, is more efficient than we've modeled. But even with those theories, there's something unsettling about it. These early black holes don't just challenge one part of astrophysics, they press against multiple assumptions. How galaxies form, how fast structures grow, how matter behaves in the early universe. If they're real, and all observations suggest they are, then something is off in our timeline. And it's not just one or two rogue outliers. We found dozens of these high redshift quasars, bright beacons powered by supermassive black holes, shining from a time when the universe was barely getting started. They're not hiding, they're loud. They're sending light across 13 billion years of space. So, the mystery isn't just that these black holes exist, it's how they grew so big, so fast, in a universe that shouldn't have allowed it. It's like finding a full-grown adult living among newborns, with no clear explanation for how they got there. It raises questions about the environment, the rules, the math, everything. And, until we can figure that out, these ultra-massive black holes will remain a cosmic riddle. A sign that, in the very earliest stages of time, something may have happened that we don't yet understand. The universe is expanding. That's not a theory, it's an observation. We've seen it. The light from distant galaxies is redshifted, stretched as space itself grows. The further away a galaxy is, the faster it seems to be moving from us. That pattern has been consistent since Edwin Hubble first noticed it back in the 1920s. It's where we get the idea of the Hubble constant, the rate at which the universe expands. But lately, something strange has happened. We've gotten better at measuring this expansion. We've refined our tools, used different methods, and now we're seeing a problem that refuses to go away. Two different ways of measuring the expansion rate are giving us two different answers. Not slightly different, not within the margin of error, consistently different. This disagreement is what scientists now call the Hubble tension. Here's the breakdown. One method looks at the early universe, It uses data from the cosmic microwave background, that ancient glow from about 380,000 years after the Big Bang. Satellites like Planck have measured it with incredible precision. Using the standard model of cosmology, scientists can predict how fast the universe should be expanding today, based on how it looked back then. That number, about 67 kilometers per second per megaparsec. The other method looks at the nearby universe, the present day. It uses type Ia supernovae and Cepheid variables, which act like standard candles. By knowing how bright these objects really are, and comparing that to how bright they appear from Earth, we can figure out their distance. Combine that with redshift data, and you get a measurement of expansion. This method gives us a higher number, around 73 kilometers per second per megaparsec. So which one's wrong? That's the issue. They both seem solid. The early universe method is based on well-understood physics and clean data. The late universe method is built on decades of observation and calibrated measurements. Independent teams have checked, rechecked, and refined both approaches. And yet the gap remains. Some scientists hoped this tension would go away with better data, but it hasn't. In fact, the more precise the measurements get, the more stubborn the disagreement becomes. It's like two clocks that should match, but the more you wind them, the further apart they drift. So now the question is shifting. Maybe this isn't a measurement problem, maybe it's a model problem. What if the standard model of cosmology, the one that includes dark matter, dark energy, and cosmic inflation, is missing something? What if we're assuming the wrong parameters? Maybe dark energy is evolving over time instead of being constant. Maybe new particles or forces were present in the early universe but faded out. Or maybe we need to rethink how gravity works on cosmic scales. There are other possibilities too. Some propose that the tension hints at early dark energy, a brief burst of energy that altered the expansion rate just before the CMB was released. Others suggest there could be phantom energy, or interactions between dark matter and dark energy that we haven't accounted for. These ideas are still speculative, but they're gaining attention because the old models aren't fixing the gap. The thing that makes this mystery so tricky is that both sides are right in their own ways. They're using different snapshots of the universe, one from its infancy, the other from its current state. It's like trying to figure out someone's life story based on a baby photo and a recent portrait, and realizing something major must have happened in between. Whatever the solution is, it's going to teach us something fundamental. Either about the nature of dark energy, the shape of spacetime, or even the origin of the universe itself. And until then, this tension sits quietly in the background of modern cosmology. Not loud, not dramatic, just persistent. A crack in the numbers that might end up changing everything. When you picture a galaxy, you probably think of something neat. A spiral like the Milky Way, or maybe a smooth elliptical blob. Those are the textbook examples. Orderly, structured, and symmetrical. That's the expectation. Galaxies are supposed to follow clear patterns, and for the most part they do. But not all of them. Out there in the deeper parts of space, astronomers have found galaxies that don't fit the mold. Some are shaped like rings, others like X's. Some twist and loop in ways that seem more like abstract art than the result of gravity and time. And the deeper we look, the more of these oddballs we find. Not just one or two rare shapes, but entire classes of galaxies that don't follow the rules. Take Hoag's object, for example. It's a near-perfect ring galaxy, an almost circular band of stars surrounding a bright spherical core. No visible arms, no bridges, just a clean ring. It looks like something that shouldn't happen naturally. And yet, there it is, hanging alone in space with no clear explanation for how it formed. The standard theory for ring galaxies is that they're caused by galactic collisions. One galaxy passes through another, like a rock dropped into a pond, and the ripple creates a circular wave of star formation. That might explain some ring galaxies, especially the messy ones. But Hoag's object doesn't look messy. It's too clean, too perfect, and there's no visible intruder nearby. No sign of the event that supposedly created it. Then there are polar ring galaxies, a galaxy with a central body and a ring of stars orbiting around it, but at a completely different angle. It's like having one spinning disk and then another one crossing over it like a giant halo. That's not easy to create. It would take a very specific kind of merger with just the right mass and momentum. And yet, we found several examples of these too. Even stranger are the X-shaped bulges found in some spiral galaxies. If you look at them edge-on, instead of seeing a smooth curve, you see a bulge in the middle shaped like an X. It turns out this may be caused by the orbits of stars trapped in a bar structure inside the galaxy, but it's not fully understood. Not all barred spirals have X shapes, and we still don't fully get why the stars arrange themselves that way. We've also seen galactic arcs, long, thin streaks of light bending in odd directions. Some of these are caused by gravitational lensing, where the gravity of a massive object bends the light from something behind it. But even with lensing accounted for, some of the shapes we see raise questions. Why are some arcs so perfectly curved? Why do some galaxies appear to stretch or duplicate themselves when there's no clear lens in sight? There's also the case of peculiar galaxies, a whole category for galaxies that don't fit into any of the usual boxes. Some have off-center cores, others have warped arms, twisted tails, or disconnected star clusters floating nearby. Many of these are thought to be the result of mergers or near misses, but that's not always easy to confirm. Space is big, and the signs of past interactions fade over time. And that brings up another problem: time. We're seeing these galaxies as they were millions or even billions of years ago. So, if something strange happened to shape them, we're only seeing the end result. Not the collision, not the chaos, just the leftovers. Trying to reverse engineer a galactic formation from a snapshot is like trying to figure out how a cake was made by looking at crumbs on a plate. You can guess, you can simulate, but you're still missing most of the story. Some researchers are starting to wonder if we're missing more than just events. Maybe we're missing physics. Could it be that under certain conditions, galaxies behave differently than we expect? Could dark matter or even unknown forces be nudging these structures into unexpected shapes? Because here's the thing. These aren't isolated mistakes or one-off curiosities. These galaxies exist. They've been imaged, catalogued. Some are even relatively close to us. And while there are theories, none of them explain all of it. Not completely. There's still a gap between what we model and what we observe. And that gap keeps growing. The more galaxies we find, the more variety we see. Not just new shapes, but new questions. Why are some galaxies lopsided when there's no obvious gravitational tug? Why do some form disconnected arms that stretch for light years and then suddenly vanish? Why do tidal streams, those long tails of stars flung out during mergers, sometimes look far too organized? These are the questions we're left with. Not because we're not trying, but because the universe doesn't always build things the way we expect it to. Sometimes it just does something weird and leaves us to figure it out. And for now, many of these structures remain unexplained. Not because we lack data, but because the answers might lie in a version of physics we haven't written yet. If you chart the motion of galaxies around us, you'll notice something odd. They're not just drifting randomly, and they're not only moving because of the universe's expansion. Instead, there's a consistent pattern, a pull. Our entire region of space, including the Milky Way, the Virgo cluster, and dozens of other galaxy groups, is being slowly tugged in a particular direction. It's not a small wobble, it's a large-scale movement, and we're not exactly sure what's causing it. This mysterious force is known as the Great Attractor. We first started noticing it in the 1970s and early 1980s. Astronomers studying the motion of galaxies realized they weren't just moving outward in a neat Hubble-style expansion. There was a bulk flow, a collective movement of galaxies toward a patch of sky between the constellations Centaurus and Norma, roughly 150 to 250 million light-years away. At first, it was thought to be an error. Maybe the measurements were off or the data wasn't broad enough. But as observations improved, the motion kept showing up. Our local group of galaxies, which includes the Milky Way, is moving at over 600 kilometers per second in that direction. And we're not the only ones. Entire clusters, dozens, maybe hundreds, are flowing along with us, as if something massive is dragging us inward. But here's the problem. We can't see what it is. The region we're heading toward lies behind the zone of avoidance, a part of the sky blocked by the thick disk of our own galaxy. There's too much gas and dust in the way for optical telescopes to get a clear look. So we rely on other wavelengths, infrared, radio, X-rays, to peer through the obscuring layer. And even then, what we see doesn't fully explain the motion. Sure, there are dense clusters in that direction, Norma cluster, Centaurus cluster, Hydra cluster, big collections of galaxies. But when we add up all their mass, it's not enough to account for the velocity we're observing. There's something more going on. Some unseen mass or some structure we haven't fully mapped seems to be at play. This led to the idea that the Great Attractor might just be a local effect, a stepping stone towards something even bigger, the Shapley supercluster. Discovered in the 1930s by Harlow Shapley, it's a massive gravitationally bound structure containing over 8,000 galaxies located farther out, around 650 million light-years away. The Shapley concentration is the most massive cluster of galaxies in our nearby universe, and some researchers believe it might be the real source of the pull. But even that's not a closed case, because the motions we observe don't line up perfectly with Shapley either. There may be other larger structures, possibly beyond what we can currently observe, contributing to this vast cosmic drift. And that raises the deeper issue. What's beyond our cosmic horizon? The part of the universe we can't see, not because it doesn't exist, but because light from that region hasn't reached us yet. If there are massive structures out there, superclusters, filaments, or even entire regions of overdense space, they could be shaping the flow of galaxies on this side of the horizon. This connects back to other mysteries. Dark flow, for example. Some scientists think the Great Attractor and dark flow might be different angles of the same phenomenon. A large-scale pull from something outside the observable universe. Not detectable directly, but visible through its effects. And yet, for all the ideas and simulations, we still don't have a full answer. The Great Attractor sits at an uncomfortable intersection between what we can observe and what we suspect exists. It's not science fiction. It's not a mathematical trick. It's real movement, confirmed, measured, and consistent. Galaxies are being pulled. We just don't know exactly why. Some astronomers are now mapping this flow with better data from radio telescopes. And new surveys like the Taipan Galaxy Survey and the Square Kilometre Array are expected to shed more light on what's behind the curtain. But for now, the tug remains a quiet but constant reminder that space isn't passive, and there are forces out there we still don't fully understand. So we keep drifting, not aimlessly, but towards something. Something big, something unseen, something that, even after decades of searching, still doesn't quite show itself, but won't let go either. Most of the universe is made up of space. That's not surprising. Galaxies may look crowded in photos, but that's just because telescopes zoom in on the densest areas. In reality, galaxies are like isolated islands, floating in an ocean of near-nothingness. But even by those standards, the Boötes Void is something else entirely. It's not just empty, it's too empty. The Boötes Void is one of the largest known voids in the observable universe. It's located in the direction of the Boötes constellation, and it spans nearly 330 million light-years across. That's not a typo. It's a region so vast that if you place the Milky Way at one end and tried to cross it at the speed of light, you'd still be traveling hundreds of millions of years later, and you'd mostly be traveling through nothing. When astronomers first discovered it in the 1980s, it was honestly a bit confusing. They were mapping the distribution of galaxies and expected to see a more or less even spread with gaps here and there. But then they hit this patch of space that seemed abandoned. Instead of the usual thousands of galaxies in a region of that size, they found dozens. Maybe a couple hundred max. It was like someone had erased a chunk of the universe. Now, cosmic voids aren't unusual. In fact, they're a natural part of the large-scale structure of the universe. Matter isn't evenly spread out. It's web-like. There are dense regions where galaxies cluster, connected by filaments, and in between those structures, there are gaps, empty zones where not much has formed. But the Boötes Void stands out because of its size. It's too big for a typical void, and its emptiness is sharper than what simulations predicted. So what's going on here? One idea is that the Boötes Void is the result of several smaller voids merging over time, like bubbles in foam, collapsing into a single large one. That could, in theory, create a supervoid. But even that scenario raises questions. Why would so many low-density regions end up in the same place? And why don't we see more voids of similar size elsewhere? Another possibility is that the void formed from a fluctuation in the early universe, a region that started out with just a bit less matter and never caught up. But that pushes against the idea of uniformity in the early cosmos. It would mean that some parts of the universe got a head start while others were left behind. There's also the role of dark energy to consider. Since it affects how space expands over time, maybe it's influencing how voids grow. Maybe areas like the Boötes Void expanded faster, thinning out more quickly than the rest of the universe. That's still an open question, though, because dark energy isn't well understood to begin with. And then there's the philosophical angle. What if this void isn't just a curiosity, but a clue? Some researchers have speculated, carefully, that voids like Boötes could be used to test alternative models of the universe. For example, theories that suggest the universe has a preferred direction, or that space might be expanding unevenly in different regions. So far, the evidence hasn't tipped the scales in favor of any radical ideas. But the Boötes Void remains a problem space. It exists, it's been observed, and it doesn't quite line up with what we expected. Some astronomers have even joked that if you were looking for a place to hide something big, really big, the Boötes Void would be ideal. Because not only is there nothing there now, but the odds of light ever reaching from something hidden deep inside that void are slim. The distances are just too large, and the emptiness is just too complete. More seriously, voids like this play an important role in testing our models. If we can understand why something like the Boötes Void exists, we get better at predicting the distribution of galaxies, the behavior of dark matter, and the subtle forces shaping the universe. If we can't, well, that says something too. For now, the Boötes Void is a reminder that not all mysteries are made of matter. Some are made of absence. And in this case, what we don't see might be the most interesting thing of all. Cosmic dust might not sound like a big deal, but in astronomy, it matters more than people think. It's in almost every galaxy we observe. It absorbs starlight, hides stars from view, helps gas clouds cool down, and plays a key role in the birth of stars and planets. In fact, without dust, most of what we think of as structure in the universe wouldn't exist, not the way it does now. But there's a strange problem. We're finding too much dust, too early. Let's start with where dust comes from. In space, dust forms from heavy elements. Things like carbon, oxygen, silicon, and iron. These elements are made inside stars, especially large ones. When those stars die, usually through supernova explosions, they release those elements into space. Over time, they clump together to form grains of dust. But here's the key part. This process takes time. You need stars to be born, live out their lives, and then die. Then their elements need to drift through space, collide, cool down, and form dust. And often, it takes multiple generations of stars for enough heavy elements to build up. In the early universe, right after the Big Bang, there were no heavy elements at all. Just hydrogen, helium, and a little lithium. The first stars, called population 3 stars, had to forge those heavier elements from scratch. So naturally, you'd expect dust to show up later. First the stars form, then the heavy elements, then the dust. That's the timeline. But that's not what we're seeing. With telescopes like ALMA and JWST, astronomers are now able to look at galaxies that existed less than 1 billion years after the Big Bang. And what they're seeing is surprising. Some of these early galaxies are already packed with dust. Enough dust to block light, obscure parts of the galaxy, and suggest a rich chemical environment. That shouldn't be possible, not that quickly. Take, for example, a galaxy like MAX 0416_Y1, located about 13.2 billion light-years away. It's one of the most distant, dust-rich galaxies ever found. It existed just 400 to 500 million years after the Big Bang. And yet, it shows signs of mature dust, meaning the kind that would normally take several stellar generations to form. So how did it get there? One idea is that massive stars in the early universe lived fast and died young, exploding as supernovae just a few million years after forming, spreading heavy elements rapidly. That could, in theory, jumpstart the dust creation process. But even with that boost, models still struggle to explain the sheer volume of dust we're seeing in these galaxies. Another possibility is that early black holes and quasars might have contributed. They can drive intense winds and shock waves that help compress gas and accelerate chemical enrichment. But again, that would require an unusual amount of activity in a very short time. And not every dusty galaxy shows signs of a quasar. There's also speculation about exotic dust sources, like pair instability supernovae, which are thought to come from extremely massive stars in the early universe. These events would produce huge amounts of heavy elements. But those stars are rare and hypothetical. We haven't confirmed their existence yet. And then there's the question of how the dust survives. Space isn't gentle. Supernova shock waves can destroy dust almost as quickly as it forms. In the early universe, radiation levels were higher, and galactic environments were more turbulent. So, not only would you have to make dust early, you'd also have to protect it. All of this leads to a quiet tension between what we see and what our models predict. Because we do see the dust, scientists measure it through the way it blocks or reddens light. They detect its emission in infrared wavelengths. The data is there. But the process behind it, the timeline that creates and preserves it, doesn't quite add up. And it's not just one or two galaxies. As our instruments get more sensitive, we're finding more and more of these dusty early galaxies. Some are extremely bright in the infrared, meaning they're full of both stars and dust. Others are faint, invisible light because they're hidden behind thick veils of dust that shouldn't even exist yet. What this might be telling us is that the early universe was more chemically active than we thought. That the first galaxies formed stars faster, lived shorter lives, and seeded their surroundings with heavy elements in a rush we didn't expect. Or it might be telling us that our understanding of dust formation, how it starts, how it survives, how it spreads, is missing key pieces. Either way, the presence of dust where it doesn't belong is more than just a curiosity. It's a sign that something in our cosmic timeline needs adjusting. The dust shouldn't be there, but it is. And until we understand why, it stays on the list of the universe's quiet, persistent mysteries. When you think of the universe on the largest scales, the word that comes up a lot is random. Not chaotic, just evenly mixed. Galaxies cluster, sure, and they form into filaments and superclusters. But once you zoom out far enough, everything's supposed to even out. No preferred directions, no special patterns, just a smooth, statistically uniform cosmos. But there's something strange going on with quasars. And it's not the kind of strange that can be brushed aside. It's alignment. Over distances that are supposed to be too large for anything to be coordinated. Quasars are incredibly bright, active galaxies with supermassive black holes at their centers. These black holes pull in matter so violently that they emit jets of radiation, shooting out across space. These jets have directions. They're not random bursts. They follow the spin axis of the black hole, and that means we can measure the orientation of a quasar by looking at the polarization of the light it emits. Now here's the weird part. When researchers looked at the polarization data from hundreds of quasars, they found that in certain regions of space, the quasars weren't randomly oriented. They were aligned. The spin axes of these black holes were pointing in similar directions, across distances of billions of light years. That's not supposed to happen. This discovery came in the early 2010s, with studies led by astronomers like Damien Hutzer-Makers. What they found was more than just a small cluster. These alignments stretched across areas of the sky larger than any known cosmic structure. Entire fields of quasars, spread out over 4 to 5 billion light-years, with their axes tilted the same way. It's like finding weather vanes in different countries, all pointing in the same direction, with no wind to explain it. So, what could cause something like this? The first answer scientists always go to is data. Maybe there's a bias in how the light is measured. Maybe interstellar dust is interfering with the signal. Or maybe there's a selection effect in how we sample the quasars. Those are fair concerns, and they've been tested. But the alignments have persisted across multiple observations, using different telescopes and different parts of the sky. If it's not a glitch, then we're left with more difficult questions. One idea is that these alignments are telling us something about the large-scale structure of the universe. Maybe there are hidden patterns, massive filaments or flows of matter that extend farther than we've ever modeled. Perhaps these structures influenced how early galaxies and their black holes formed, nudging their spins in the same direction over time. That's speculative, but it would be a way to connect the dots without rewriting all of physics. Another possibility is that there's something about the initial conditions of the universe that left behind this imprint. Something during the inflationary period. A brief moment right after the Big Bang, when space expanded faster than the speed of light, might have set up directional features that only now show up in the orientation of these distant objects. There's also the idea that this is a topological feature, something about the shape or fabric of the universe itself. Maybe space on the larger scales isn't as smooth as we thought. Maybe there's curvature or twists or something else embedded in the structure of space-time that we haven't accounted for. And then, of course, there's the big unknown. Maybe this is the beginning of something we haven't even begun to define. A signal, not of communication, but of cosmic structure that breaks our rules. Whatever the case, these quasar alignments are hard to ignore. They challenge the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. If that principle breaks down, it could mean rethinking not just how galaxies form, but how the universe is shaped at the highest level. So far, there's no consensus. The alignments are real, the explanations are few, and the implications are wide open. And the fact that we're still trying to explain why objects billions of light years apart are acting like they coordinated their spin axes, that tells you just how little we truly understand about the largest canvas there is. According to everything we know about physics, the Big Bang should have created equal parts matter and antimatter due to the principle of symmetry in fundamental interactions. At the earliest moments, within the first 10 to the power of minus 36 seconds, the universe was in a state of thermal equilibrium at extremely high temperatures, above 10 to the power of 27 Kelvin. During this epoch, particles and antiparticles were constantly created and annihilated in equal quantities. For every proton, there should have been an antiproton. For every electron, a positron. The laws of physics don't show any strong preference for one over the other. They treat matter and antimatter almost identically, and yet here we are, a universe made almost entirely of matter. Antimatter is gone. That's not just an odd detail, it's a massive inconsistency, because when matter and antimatter meet, they annihilate each other, completely. They release energy, and nothing remains. So, if the early universe had equal amounts of both, they should have cancelled each other out. No stars, no galaxies, no atoms, just leftover radiation. Clearly that didn't happen. Somehow matter won, and we still don't know why. This is known as the baryon asymmetry problem, and it's one of the biggest open questions in modern physics. Why did the universe end up with a surplus of matter? There are a few ideas, but none have been confirmed. One possibility is that in the early universe, some tiny imbalance occurred, maybe one extra matter particle for every billion pairs. That sounds small, but it would have been enough. When the matter and antimatter annihilated each other, that leftover sliver of matter could have gone on to form everything we see today. Every star, every planet, every living thing. So, where did that imbalance come from? Some theories point to a process called CP violation, a breakdown in the symmetry between matter and antimatter under certain conditions. We've seen hints of it in particle physics experiments. Certain particles, like kaons and B mesons, behave slightly differently than their antimatter counterparts. But the amount of CP violation we've observed isn't nearly enough to explain the huge imbalance in the universe. Others suggest that during cosmic inflation, some asymmetry might have been baked into the structure of space itself, or that unknown particles or forces, possibly related to grand unified theories or supersymmetry, might have created a bias toward matter in the earliest moments. There's also a more speculative idea. Maybe entire regions of the universe are made of antimatter, and we just happen to live in a matter-dominated bubble. But if that were the case, we'd expect to see gamma rays from matter-antimatter annihilations at the boundaries between those regions. And we don't. The observable universe seems to be entirely matter, all the way through. Physicists are still looking. Particle accelerators like CERN are running high-energy experiments to detect rare interactions that could reveal new sources of CP violation. Cosmologists are scanning the sky for any trace of asymmetry in the cosmic microwave background that might hint at how matter came out ahead. But so far, the answer remains out of reach. And that's what makes this mystery so strange. It's not about some distant galaxy or exotic object. It's about everything. About why anything exists at all. Because if matter and antimatter had truly been equal in the beginning, the universe would have ended almost as soon as it started. No atoms, no light, just emptiness. So somewhere, something broke the symmetry. Something tipped the balance, just enough for all of this to exist. We don't know what it was, but whatever it was, it made the difference between a blank universe and a living one. When we think of empty space, we imagine nothing, a perfect vacuum. No air, no dust, no atoms, just silence. But in physics, especially quantum physics, that idea doesn't really exist. Because according to everything we know, even empty space is never truly empty. It's constantly buzzing with activity. Tiny particles pop in and out of existence, borrowing energy from the vacuum, existing for a brief moment, and then vanishing again. These are called virtual particles, and they're not just theoretical, they show up in real, measurable ways. This is what we call the quantum vacuum, and it might be one of the most misunderstood and mysterious concepts in all of modern physics. Let's break this down. According to quantum field theory, every field in the universe, electromagnetic, gravitational, strong, weak, is present everywhere in space. Even in the places that seem empty, these fields exist. And due to the uncertainty principle, there are always fluctuations, small blips of energy that can create temporary particles. These fluctuations are random. They can't be predicted in detail, but their effects can be measured. For example, take the Casimir effect. If you place two metal plates very close together in a vacuum, so close that only certain wavelengths of energy can exist between them, those plates will experience a tiny force pulling them together. It's not from gravity or magnetism, it's from the vacuum itself, from the difference in quantum fluctuations inside and outside the gap. And it has been measured in the lab. Another example is the Lamb shift, a tiny change in the energy levels of electrons in hydrogen atoms. It's caused by interactions with the quantum vacuum. Again, real, measured, and explainable only with quantum field theory. But here's where the mystery comes in. When physicists calculate how much energy should exist in the vacuum, how much energy these fluctuations should contribute to the structure of space, the numbers go off the charts. Way off. The predicted energy density of the vacuum is around 10 to the power of 120 times greater than what we actually observe. That's not a rounding error. It's the largest known discrepancy between theory and observation in all of science. This problem is so well known that it has its own name: the vacuum catastrophe. In simple terms, quantum theory says empty space should be overflowing with energy. But observations, especially the rate of the universe's expansion, say it's almost empty. So either something's wrong with our theory, or something even weirder is cancelling out all that energy. This links directly to dark energy, the mysterious force that seems to be driving the universe's accelerated expansion. Some physicists think dark energy is just vacuum energy. Others think it's something separate, but in either case, we don't understand the vacuum. Not fully, and yet it fills everything. There are deeper questions too. If space is always fluctuating, could those fluctuations give rise to entire particles? Could they seed new universes? Some speculative models suggest that universe creation could happen in a quantum vacuum under the right conditions. Meaning even if our universe ends, the vacuum remains active, creating, evolving, pushing out new spacetime bubbles. And then there's the philosophical side. If nothing is never truly nothing, does true emptiness even exist in physics? Or is what we call nothing just a lower energy version of something very real? The quantum vacuum problem sits quietly underneath a lot of modern cosmology. It shows up in particle physics, in relativity, in field theory. And yet, we still don't fully get it. Why is there so little vacuum energy in practice when theory says there should be so much? What is the vacuum really made of? And is this nothing actually where everything starts? We don't know. But what we do know is this: empty space is one of the most active, confusing, and important ingredients in the entire universe. And the more we study it, the more it challenges our idea of what nothing even means. In theory, we know how the early universe made its first elements. Right after the Big Bang, the universe was hot and dense, perfect conditions for nuclear reactions. This period, called Big Bang nuclear synthesis, lasted only a few minutes, but during that time it forged the first atomic nuclei. And the results of that process are pretty well known. We should end up with about 75% hydrogen, 25% helium, and tiny traces of lithium, deuterium, and a few other light elements. The exact amounts can be predicted very precisely using physics and the known conditions of the early universe. When we check observations of hydrogen and helium, the numbers match. The predictions line up with what we see in ancient stars and in interstellar gas clouds. That gives us confidence that our models of the early universe are basically sound. But then there's lithium. According to theory, we should see a specific amount of lithium-7, the most stable isotope left over from the Big Bang. Not a lot, but enough that we should be able to find it in the oldest stars in the universe. These stars, called population 2 stars, formed very early, before much stellar processing could destroy or add to their chemical makeup. So, when astronomers look at those stars, they expect to find lithium levels that match predictions. But they don't. What they actually find is that the lithium is missing. The amount of lithium-7 detected in old stars is only about 1/3 of what the standard model predicts. That might not sound like a huge gap, but in cosmology, where predictions are accurate down to decimal points, that's a major discrepancy. This mismatch is known as the cosmological lithium problem. And it's not a simple case of observational error. This has been checked for decades, using different stars, different instruments, different measurement methods. The lithium is consistently lower than expected. And that's a problem because it means something in our understanding of the early universe is wrong. or incomplete. One possibility is that the lithium was destroyed in stars over time. Maybe even the oldest stars aren't quite as pristine as we thought, and some process inside them is reducing the lithium. That's plausible. Lithium is fragile. It burns at lower temperatures than other elements. But models of stellar interiors suggest that this kind of depletion shouldn't be enough to account for the full gap. It might explain a little, but not all. Another idea is that the nuclear reaction rates used in the models are slightly off. Maybe one of the key inputs in the Big Bang nucleosynthesis calculations, like how often certain isotopes fuse or decay, is incorrect. But the nuclear physics involved has been studied in labs extensively. Adjusting those numbers would also throw off the predictions for other elements, like deuterium or helium, which currently match observations well. So that fix would solve one problem, but create others. Some scientists have even suggested new physics. Maybe there were exotic particles, like axions or decaying dark matter, that interacted with the early universe in a way that altered the amount of lithium produced. That would be exciting, but there's no direct evidence for any of these particles. It's still speculation, without a solid foundation. And then there's the more radical idea: maybe our understanding of the early universe itself needs tweaking. Perhaps the conditions right after the Big Bang weren't as uniform or well-behaved as we assume. Or maybe there were small pockets of variation that affected element formation differently in different regions. That would imply the universe wasn't quite as homogeneous as the current model suggests. At the end of the day, the lithium problem remains one of those quiet, persistent gaps between theory and reality. It doesn't break the standard model entirely. It doesn't throw physics into chaos. But it sticks out, just enough to be uncomfortable. And in science, those little gaps matter. Because sometimes it's the small inconsistencies, the things that don't fit, that lead to the biggest breakthroughs. Right now, scientists are still looking for better data, better models, or better theories. But until then, lithium, one of the lightest, simplest elements in the universe, is holding onto a mystery we haven't solved. There's a number in physics that shows up everywhere. It's dimensionless, meaning it doesn't depend on any particular unit like meters or seconds. It's just a pure ratio, and it seems to define how strongly charged particles like electrons and protons interact through the electromagnetic force. That number is called the fine structure constant, and its value is approximately 1/137. The fine structure constant, often denoted as alpha and approximately equal to 1/137, was first introduced by Arnold Sommerfeld in 1916. Sommerfeld, a German physicist, developed this dimensionless constant while extending Niels Bohr's model of the atom to account for relativistic effects and the fine structure of atomic spectra, particularly in hydrogen. This precise value shapes physical phenomena from the stability of atoms to the formation of galaxies, underscoring its control over much of the universe's structure. It's one of those constants that we just measure. We plug it into equations. We use it in everything from quantum electrodynamics to atomic structure to particle physics. But for all its usefulness, we don't know why it has the value it does. And we don't know what it would mean if it were even slightly different. Physicist Richard Feynman once said that the fine structure constant is one of the greatest damn mysteries of physics. He called it a magic number that comes to us with no explanation, and he wasn't exaggerating. Because this one number seems to control a huge amount of the structure of the universe. It determines how atoms are built, how tightly electrons orbit nuclei, how light and matter interact. If this number were a little larger, atoms wouldn't hold together. If it were smaller, chemistry would change completely. The universe, as we know it, might not exist. And yet, for all that weight, it's just there. No theory currently explains why the fine structure constant has the value it does. It just shows up. Some physicists have tried to link it to other constants. like the speed of light, Planck's constant, or the charge of the electron, but there's no equation that fully explains it. It's like a dial that was set, and we don't know who set it or why. Even stranger, there are ongoing studies suggesting it might not be constant at all. Astronomers looking at the light from distant quasars have found very slight variations in the fine structure, constant over billions of years. The idea is controversial, and the data isn't fully confirmed, but if it turns out to be true, if this number is changing over time or across space, then that would shake up a lot of what we take for granted in physics. A varying fine structure constant could point to new physics, hidden dimensions, unknown fields, or interactions we haven't accounted for. It might even help explain why our universe seems so perfectly tuned for life. And that leads into the larger question. Why is the universe so finely balanced? Why do so many constants, mass of the electron, strength of gravity, charge of the proton, fall into exactly the right range for stars to form, for atoms to exist, for biology to even be possible? Some scientists say it's a coincidence. Some say it's the result of anthropic selection, the idea that we can only exist in a universe where the constants allow us to exist, so it's no surprise we find ourselves here. Others think there might be deeper laws we haven't discovered yet, laws that explain not just how things work, but why they have the values they do. The fine structure constant sits right at the center of that mystery. It's not just another number, it's a doorway, a signpost, a quiet reminder that we don't fully understand why the universe works the way it does. And maybe we never will. Maybe 1/137th is just part of the wallpaper of reality, something we can measure, use, and live with, but never truly explain. But the fact that this number is everywhere, from particle accelerators to the light in your room, and we still don't know where it comes from, that's worth paying attention to. For decades, scientists have believed that dark matter is essential for galaxy formation. It's supposed to be the invisible scaffolding, the hidden mass that holds everything together. Without dark matter, galaxies shouldn't have enough gravity to form in the first place. The stars would drift apart, the structures wouldn't last. But then we found galaxies that seem to break that rule completely. Galaxies with little or no dark matter at all. The first major case was NGC 1052-DF2, discovered in 2018. It's a diffuse ghostly galaxy located about 65 million light-years away. It has stars, it has globular clusters, but something was missing. When astronomers calculated its mass, they realized it didn't match expectations. The visible matter, the stars and gas, accounted for almost all of it. That was strange. In most galaxies, dark matter makes up 10 to 30 times more mass than the visible stuff. But in DF2, the numbers didn't add up. There was hardly any dark matter. It was like someone had built a galaxy without the hidden framework. And it wasn't just one mistake. Follow-up studies using different methods confirmed the finding. And not long after, astronomers found a second one, NGC 1052-DF4. Same type of galaxy, same issue, very little dark matter. So, what's going on? One theory is that these galaxies formed in a unique way, possibly torn from a larger galaxy during a collision, leaving them stripped of dark matter. That might explain the lack of invisible mass. But even that doesn't fully hold up. Simulations show that even in tidal interactions, some dark matter usually remains. Another idea is that these galaxies never had much dark matter to begin with. Maybe they formed from clumps of ordinary gas that somehow bypassed the usual formation process. But that runs counter to everything we understand about cosmic structure. Dark matter isn't just optional. It's been considered necessary to get galaxies in the first place. And then there's the possibility that something's wrong with how we detect dark matter. Most of the time, we infer its presence by measuring how fast stars are moving. If stars in a galaxy are orbiting too quickly for the visible mass to hold them in, we assume there must be extra unseen mass, dark matter. But in galaxies like DF2 and DF4, the stars are moving slowly. Their motion matches the visible mass almost exactly. That could mean there's no dark matter, or it could mean we're misunderstanding the physics of motion in extremely low-density environments. There are also deeper, more radical ideas. Some suggest this could point to flaws in our theory of gravity. That maybe in regions with very low acceleration, like the outskirts of diffuse galaxies, gravity behaves differently. This is part of what's called MOND, modified Newtonian dynamics, an alternative to dark matter that changes the laws of motion at large scales. Most physicists still prefer the dark matter explanation, but findings like this keep MOND in the conversation. Whatever the cause, these galaxies are hard to ignore. They exist. We've seen them. And their properties don't match the dominant model. That doesn't mean the model is wrong, but it does mean something is missing. Either these are rare outliers that formed under strange conditions, or they're clues pointing to a bigger oversight in our understanding of the universe. And here's the twist. At the same time, we're finding galaxies without dark matter. We're also finding galaxies made almost entirely of it. Galaxies with almost no stars. Just clouds of invisible mass holding them together. So on one end, we have galaxies with too little dark matter. On the other, galaxies with too much. And in between, a theory that's still being stretched in every direction. That's what makes this mystery so compelling. It's not just about numbers or measurements. It's about how galaxies form, how gravity works, and whether our picture of the universe is complete. And for now, these dark matter-free galaxies are like cracks in a wall. Small, rare, maybe even explainable, but enough of them, and the whole structure might need to be looked at again. Out of everything we experience, time feels like the most obvious. It moves forward. 1 second follows another. Yesterday's behind us, tomorrow is ahead, and we all move through it at the same pace, or at least that's how it seems. But the more we study the universe, the less certain we are that time works the way we assume. In fact, some physicists are beginning to think that time itself might not be fundamental. That it's not a basic building block of reality, but something that emerges from deeper processes, like temperature or pressure. That sounds strange, but the signs have been here for a while. For one, time doesn't behave the same way everywhere. According to Einstein's theory of relativity, time slows down near massive objects like stars and black holes. It also slows for objects moving close to the speed of light. These aren't just theories, they've been tested with atomic clocks flown on airplanes, placed on mountaintops, or sent into orbit. The clocks tick differently depending on where and how fast they are. In daily life, we don't notice it. But across large distances, or under extreme conditions, time bends. It stretches. It shrinks, which means it's not absolute. Then there's quantum physics. At the smallest scales, the laws of nature are time-symmetric. They don't care if time moves forward or backward. If you recorded a quantum process and played it in reverse, the math would still work. Nothing breaks. That's very different from how we experience time, where eggs break but don't unbreak and memories always point backward, not forward. So where does the arrow of time come from? Why do we remember the past, but not the future? Why does heat flow from hot to cold, and not the other way around? The most common answer is entropy, a measure of disorder. In thermodynamics, systems tend to evolve from low entropy, ordered, to high entropy, disordered. That's where the arrow of time seems to come from. It's not that time moves, it's that entropy increases and we move with it. But even this explanation depends on one big assumption: that the universe started in a low entropy state. Why it did that? No one really knows. That question takes us right back to the origin of the universe, and we don't have a complete picture of what happened then. There are also questions about whether time had a beginning at all. If the universe started with the Big Bang, then time, at least as we know it, may have started there too. But what if the Big Bang wasn't the beginning? What if it was just a transition, or a bounce, or part of a cycle? Does time go back further? Or loop? And then there's the possibility that time doesn't exist at all. Not in the way we experience it. In some quantum gravity theories, time doesn't even appear in the fundamental equations. It's something that shows up only when enough particles interact in specific ways, when there's a system big enough to allow for change and measurement. Just like temperature doesn't exist in a single molecule, but emerges when you look at trillions of them vibrating together. There's even a view called block universe theory, which suggests that the past, present, and future all exist at once. Time doesn't flow. Instead, everything that ever happened and ever will happen just is. Our experience of moving through time is an illusion, like flipping through the pages of a book that's already been written. Of course, not everyone agrees. Some physicists argue that time is real and fundamental, and we just don't understand it fully yet. Others say it's emergent, tied to our brains and biology, or to the thermodynamic behavior of matter in bulk. But across all these views, one thing is clear: time isn't simple. And that makes it one of the most important open questions in all of physics. Because time isn't just something we measure, it's something everything depends on. Motion, causality, life itself, it all flows through time. If time is emergent, or if it behaves differently under certain conditions, then our whole understanding of cause and effect might be resting on assumptions that don't hold up everywhere. The mystery of time might not come with dramatic visuals or strange telescopic findings, but it runs deeper than most. It sits beneath every observation we make. It shapes how we experience the universe. And it may be, ironically, the last thing we truly understand. We like to think we've figured the universe out, we've named the particles, mapped the galaxies, built models to explain almost everything. But then, you look a little closer, and the questions start piling up again. A cold patch in the sky that defies statistics. A star that dims like clockwork, with no known cause. Black holes that formed too early. Galaxies missing dark matter. Signals we can't trace. Constants we can't explain. And patterns in the background radiation that shouldn't be there at all. For every answer we find, something else doesn't fit. And maybe that's the point. The universe doesn't owe us explanations. It's not here to make sense on our timeline. But the fact that we can even ask these questions, that we can detect a supervoid, or measure the tilt of a quasar, or wonder where the antimatter went, that tells you something. It tells you that we're not done yet. These mysteries don't mean we've failed to understand the universe. They mean we're still learning, still uncovering the pieces, still chasing the truth, even when it changes shape the closer we get. And maybe, just maybe, the unknown is the most honest part of the whole thing.